talk about today, kind of our approach, the Quantum Labs approach to how we see quantum technologies and how we want to address it. Just some short points beforehand, if everyone could shut off their videos and make sure that the mics are off so we don't have any feedback. That would be amazing. We'll do it in regards to questions. We have also tried to make it interactive, but we are open. If anyone has a question, just raise your hand, and we want to just keep it as interactive as possible. So yeah, we want those discussions, we want those questions. Feel free to just raise your hand and we'll call you. And other than that, just short introduction. My name is Iftikhar Ahmed. I work for the Quantum Lab as a go-to-market lead and lead our quantum advisory team in the Quantum Lab. And I'll do the presentation or do the talk together with Julian. And I'll give over to you, Julian.
Perfect. So thank you, Ifti. So my name is Julian van Velzen. I lead the Quantum Lab, and so I work together with Ifti, but also many other colleagues and brilliant people to all with the same aim, which is really to make quantum computing applications a reality for our clients in the next couple of years. So maybe let's just dive straight into this. Why are we talking about this today, about this path to value, Ifti? Maybe I go straight to the next slide as well.
Yeah, for sure. And I think it has, obviously, we in the Quantum Lab have been talking about that for a while, but now it's becoming more and more a reality. So what you see here is the development roadmap of IBM. So IBM has published how their quantum computers are developing. And a lot of what is very promising is that all the promises or all the targets that they had for their hardware, they are hitting. So we are getting to a point where we are getting hardware that can actually do something that has value for us. And I think that's really the main goal. And that's something that has really pushed the whole field forward and made it possible for us to see where this quantum value could come from. And I think this, together with the QEra announcement, was really what made it interesting. Perhaps you can talk a bit about that QEra announcement, because I think the QEra announcement is still very much discussed if it's really something that's interesting or not.
Absolutely. So on the one hand, there's these roadmaps from companies like IBM that provide a lot of confidence in their roadmap, because they committed to their roadmap time and time over again. But on the other hand, there's these startups that are doing these things that are, maybe we can trust them as much as we can trust IBM's, but if they are right, they may accelerate things even more. And so this announcement by QEra is that they show that even in 2026, so that's already very close, of course, they would have machines that are capable of 100 qubits that are error corrected up to a level where they can run millions or maybe even hundreds of millions of gates. And so that would firmly put us within a regime where we can actually start to use them, right? It won't be in an area where everything is possible with a quantum computer, but definitely some applications will become commercially relevant. And so what is interesting is that the conversations that we have had over the past years are starting to change now, because it always was something, this is future interest, this is one day technological interest, and now it's changing from, okay, if this is really in 2 years, how are we going to prepare? How are we going to look from this end to end? How are we going to make sure this will actually work in practice, and how do we do not leave behind, right? So I think that conversation is starting to change. And I think that we have this conversation with loads of different clients. There are many different potential applications, but really in quantum chemistry is one of the most clear path towards value. So let me go to that next slide. What do you think, Ifti? Do you agree with quantum chemistry as a key application?
Obviously, I think we have in the Quantum Lab, we've been really concentrating on where we think is the most value and the most near-term value. And so that has been really the chemistry field, the material science field, right? So everywhere where we can use chemistry, those are fields that are already huge and have a major impact on anything that we do today. But interestingly enough, those are also the fields that really offer themselves towards quantum computing, since quantum chemistry is obviously very native in the simulation of molecules and the simulation of specific parts of a molecule are very native to what a quantum computer is really good at. So if we can really do those simulations on quantum computers and get some kind of value and some kind of predictive features out of that simulation that we can then feed back into our pipelines, we can expect a value in a near term. And so that is really, and I think the whole community is on the same page, that this is something that where the first value out of quantum computers will be. And interestingly enough, this area touches like so many different of the use cases that are super interesting for us as a company, and that we have been exploring also on a classical side. And perhaps you can talk a bit about a few of those use cases, because I think that's really where it gets really interesting.
Right. So sometimes I think that colleagues think about chemistry as, this is not our key business, right? We're a big part of Capgemini, of course, is an enterprise IT solutions firm, but chemistry is really impacting many of our clients, right? So it is impacting automotives, it's impacting pharmaceuticals, energy utilities, and of course, part of that is sort of research into using quantum chemistry tools. But really, in the end, it's about large-scale transformation of these industries at large. And so there will be many parts of Capgemini that will be relevant to these use cases.
And so, Julian, just if I can add to that, just let's not forget climate tech, because I think we as a company have been really pushing forward into different fields of like sustainability. And it's very interesting that how much it lends itself actually to that sustainability field.
Absolutely. So maybe one of the key messages that we wanted to get across in this talk is, well, one that we shared is that it really could be on the horizon, but the second is that to really get there, it's not going to be easy. To implement quantum computing requires so much more insight, so much more clever solutions, so much more connection and integration of different technologies all together. And I think that's really where a key strength should be to integrate this across different skills. But just to name sort of a couple of challenges along the way. So on the one hand, quantum computers are noisy, right? So they can only run a certain number of gates before they run into trouble. And even though chemistry is maybe one of the most high potential areas, we quickly run up to hundreds of thousands or even millions of gates in a circuit. And that is really far beyond what a classical computer or a quantum computer can do these days, right? So we need significant improvement in the hardware over the next couple of years before this could work. But then I would say that even if we have better performance hardware, often our clients are not necessarily directly interested in, directly the results of a quantum computer. So, for example, if you're able to calculate some ground state energies, or you're able to calculate some time evolution of some electron system, that is not the thing that they're interested in. What they're interested in is trying to identify, what are potential drugs, what is the reactivity, is something toxic or not. And to be able to address that, you will most likely need a combination of both quantum computers as well as classical computers, right? So that integration is really essential, so that we work on that. And I think third, even if that were to work, for some reason companies aren't always able to find the right applications that make this worthwhile, right? So, for example, we work a lot with pharmaceuticals. They are not really, the key focus usually is small molecule drug design. Even though there's a whole range of medicine out there that could have a lot of value. And so the question is, why not? And how can we make sure that they do find the use case that are good enough and that will help them to adopt it? I think what we wanted to talk about mostly is this third part of the question. right? So we have the hardware, we have sort of the use case and how it integrates with classical solutioning. But I think what is really interesting at the stage where we are now today is to think about what really are those use cases that are good enough, that are valuable enough, that companies care about, and that companies want to implement. What do you think, Ifti? Maybe we can also, in sake of time, skip a little bit the sort of the technical solutioning and go first into asking to the audience what they think about this, right? So we discussed there's these different challenges along the way. There's the business case that we have to work out and finding the right application. There's the challenges on the workflow and how that works, and then there's the limited hardware. What do you guys think? Is there one challenge that's more challenging than the other? What do you think, Ifti? Probably let's first see what the audience thinks. I see a question. I see your hands.
Hi, this is Edmundo. Hi, I've also had a couple of discussions with some colleagues from Microsoft on this area, and the problem that I see is currently that it's not ready for companies yet to be used as such. Hardware implementation is very expensive and there is not that many algorithms still being developed for it, so it's not actually really well for production. Actually, the companies are still doing some kind of competitions to see who can find algorithms and stuff. So it's still very early stage. I don't see currently the potential to actually market it also within companies. Of course, it's great to be in there learning and getting prepared for it, but it's hard for me to see the business value currently directly into our customers.
So yeah, so I think you're right. It's absolutely still a research topic. I would say that we are getting closer to a valuable quantum computer. So if we can trust these roadmaps from QEra, for example, it's only in 2026 where the hardware specifications will be good enough for commercial applications. I think it's also for a reason that Microsoft says that it's probably longer away because they don't have any quantum hardware, right? So if you ask IBM, they would give probably a different answer. But you're right, it's still early stage because none of these computers are adding any value today. I would think that one of the key challenges that we and that Ifti mostly thinks about is that even though, well, maybe you can say that better yourself, right? You said it very well this morning.
Yeah, I think it's very interesting because what you just described is exactly this question of like, where is the business case for it, right? Is the business case there right now? And interestingly enough, yes, it is research, but also we are doing research in regards to understanding how that business case looks like. And so that's what kind of our advisory team is really working on. Because sure, we can work with companies, and one big part of it is working with companies to help them understand quantum computing, help them prepare for quantum computing and quantum tech as a whole. But one big part is also us internally understanding how we can actually create value out of the work that we are doing. And so there are three different things that we in that regard concentrate on, which is really figuring out the value of the technology. So what is it that the technology can do by when, and how can it be valuable? So in that we have done different kinds of projects or looked at different kinds of opportunities. So for example, cost advantage of a quantum computer. So there is the idea that a quantum computer for some calculations could have a better cost advantage, also it could save energy in regards to classical compute. So for specific use cases, it could have value already in the near-term future to use that as a business case. Why would you address quantum computing right now? Why should you think about quantum computing? But then what is much more interesting is the actual use cases. So we have concentrated on 4 use cases that we think are the most valuable use cases. And for those use cases, we are really creating, thinking about what is the downstream value of the work that we are doing today. So Just I think we have in the next slide, perhaps, Julian, we have the 4 use cases also listed, if I'm not wrong.
Yeah, maybe very quickly. I thought that Armin had a follow-up question.
Oh, sorry.
Or was I mistaken? I thought you...
No, but I would like to add, I totally agree with what you're saying. I also find it really interesting. I think the only business case for me, in my view right now, which is really where a lot of companies should invest in, is security. Because when a company knows how to use it, they will be able to crack all codes relatively quickly. So actually, if there's one business case, is actually data security and business security on the long term, preparing already before the technology is ready to be used.
So we have a part in the Quantum Lab that just looks at security, and there was just mentioned earlier a bit that this is something that's very much picking up recently. So here specifically we are talking about the quantum computing part. Obviously, quantum security is a topic in itself that we can talk about, and for sure has a big business case. And for us, it's to figure out, one of our works is to figure out how do we address. It's not, and nobody's saying that we have to right now go to clients and sell them quantum computing, but it is the case that a lot of clients do need to start with it and are starting to understand that there is value in understanding quantum computing and quantum computing use cases that are specific to their business and what they can do with it, because those are also use cases that will be disruptive, and those are like use cases that have massive potential to be a competitive advantage to them. And so looking at those use cases is something that has relevancy today also for them.
So maybe we can dive into some of the use cases. So one of the key areas that we are looking at, for example, there are 4 key areas that we're looking at. One of them is batteries, battery research. Another one is research into corrosion chemistry. A third one is drug discovery, and in particular, it's certain type of metalloenzymes. And the fourth one is carbon capture materials. So I think the next slide is about batteries. So maybe Ifti, why can you share, sort of illustrate based on the points that you mentioned before, why do people care about researching batteries today with quantum computers?
I think it's everybody knows that batteries have like a massive impact in regards to not only the automotive sector, but especially energy sector, energy grids. All of that is all kind of very much based on the how good our batteries are and how much we can make them better over time, so that they don't degrade as fast, that they have longer life cycles. All of that plays a big role into not only having the amount of energy that is needed, but also in regards to sustainability aspects of not having as much waste, not having having batteries, using more of kind of batteries and less other kinds of energy creation mechanisms. So all of that plays a big role. And right now in the battery space, there is this idea that a lot of the chemistry that happens in the battery is still not very well understood. So there is still a lot of spaces where it's not fully we are not fully able to simulate them to a degree that we would want to really get to better solutions, find the right materials, find the right materials for the cathodes, for the anodes, and how they work together to really get the optimal solution. And there, one of the big use cases could be to look at specifically quantum chemistry and how quantum chemistry could play into that. And that's what we did with the QASys project. And perhaps you can talk a bit more about the QASys project itself.
Absolutely. So the idea here was to really find the key specific applications within battery research that have potential for quantum advantage. And so we try to base it on 3 criteria. So one criteria is, will quantum computer provide a higher accurate solutions to some property? Second, is that property relevant to us? So for example, there is in many batteries there's transition metals. transition metals are very difficult to calculate classically because they got very complicated very complex shells and orbitals. So it's very difficult to simulate them with classical solutioning like DFT. But is it also relevant for the industry, right? So that's and there are many cases within batteries where it is interesting because they severely limit the capacity of a battery. But very often it's also not the case, right? So trying to figure that out is the second criteria. And then the third criteria that we had was really, can we build an approach where we combine quantum simulations at small scales, where we start to simulate maybe only a fraction of a molecule, build it up over time such that we have a scalable network, and where we then connect that with machine learning to really predict properties that will help companies to build better batteries. And in particular, we have identified a few different use cases here. So one use case is electrolyte decomposition in cathode materials. So basically what this means is that there's large electrolyte molecules. They bind to the surface of the cathode, which is a catalytic. There's a reaction catalyzed by the transition metal in the cathode, which would then further degrade the cathode materials. So this is a very complex, not very well understood process, and it's complex for a number of reasons, right? Because on the one hand, we have these transition metals that are hard to understand. Second, we have a larger quantum chemical molecule that we need to simulate in to some degree, but we also have a very complex electrolyte solvent that has all kinds of mixtures of additives and all kinds of things added to it, which also impact the solution. So what we really need is to have some sort of a model where we use quantum simulations for the reaction centers, that is very high accuracy solvers, use other quantum chemistry solutions to treat the larger part of the molecule, and use other solutioning such as molecular dynamics to simulate additives and other elements to the solvents. Right, so really breaking this up into many different areas. And so this is one of the use cases. The other use case we identified was degradation of electrolytes themselves identify degradation of electrolytes. And third, looking at voltage decay in stack layers of cathode materials. So each of those really share those characteristics where it's hard to simulate them without a quantum computer, but where we also think that there could be a path towards value if you do so.
And I think just to add to that, so we have also in those projects, what we really try to concentrate on is to bring them together with clients. So we always talk about like application centric data or application centric research that we want to do. In that regard, that the research that we do, we really combine it with clients to find the use cases that are relevant to them and that have an impact on their business and their day-to-day. So for each of the use cases that we are also talking about today, we have accordingly some clients that have shown interest and that are supporting us in doing this project. So for example, for the battery space, we are in talks with Saft, who's the big battery company out of France. We are in talks with VW, who are supporting this project. So that is really one big part of our kind of approach to those projects.
Absolutely. And so maybe one final point to illustrate why this is so complex. And I think that this, for example, shown by the idea that Tesla still catch fire every now and then, right? Even though they have been produced for a very long time, and there's been models for for everything that you can model, they still catch fire. And so if we were able, and that's because we don't understand these systems well enough. If we were able to better understand the chemistry that's going on, we might make them safer. And of course, the same holds for other examples. For example, why has it taken already 20 years since the first idea of lithium metal batteries, and we still haven't had them on large scale, right? Because all kinds of complex chemistries happen. We see, for example, electrolyte dendrites form in the electrolyte that cause short circuiting and having all kinds of safety hazards. So really trying to understand these processes will help these companies speed up their product life cycle and help them bring these products earlier to market. So even though it's sort of a research topic, I think that's why many of our clients are interested in this today. Maybe let's move on to a second use case, which is I think one of the key ones for us, which is predicting properties of therapeutics. What would you, in your words, Ifti, be the reason why companies are exploring these topics today?
I mean, for drug discovery, it's actually pretty straightforward. So anybody who works in the drug discovery field knows that doing drug discovery has a long life cycle. So it takes a long while until you get to a point where you can actually bring a drug towards the market. And there gets so much research and trillions of dollars every year into that process and into optimizing that process and doing a lot of research. And still, there is a lot that has to be done in the labs. There is still a lot that has to be done physically by some researchers. And so the ideas behind the drug discovery process is really to understand how much of this process can we actually simulate, and would it be possible to use quantum computers to really optimize this process to a way where it would make it much shorter. And I think the use cases are out there already with, if we just think back 2-3 years with when COVID came and the vaccine, that was already a very fast turnaround for a vaccine. But still, how long does it take for us to actually have a vaccine? So those kinds of processes to really figure out how can we optimize them, how can we simulate more of the chemistry so we don't have to test everything and do everything manually. That is really the key for the life sciences sector. So that was always the kind of area also that companies like GSK, with whom we did this project, were super interested in. If they can get some value out of quantum computing for this field, that will have a massive impact on their business as a whole. So I think the life sciences sector also has like a very interesting use case for it, and some use case that they have been looking for better solutions for forever. So that was the really interesting part of I think this project.
Right. So I think maybe one of the key points is that now that the quantum computers are getting closer to maturity, and it definitely is still a research topic for the next couple of years, but at least the path towards value is getting clearer. It shows that for companies to be able to leverage quantum computing for such applications, it's more than just a technical challenge. What we saw here was that, well, for a large group of clients, probably, for a large group of molecules, probably a quantum computer won't help much. But for newer types of drugs, for example, those based on transition metals, it's not, there isn't really a pipeline as of this moment. And so trying to get these solutions and these tools into production requires not just a change of technology and technology maturation. It also really requires companies to rethink their business and to rethink the way they adopt these technologies. I see there's a question, Francois. You have your hand up.
Oh, no, sorry, it was the wrong button. I just didn't put something in the chat. I have to leave.
Okay.
I will watch the transcript or the recording. Yeah?
Perfect.
Thanks very much.
Day. Bye. So yeah, so really it's as we growing closer, it becomes more not just a technical challenge, but also really an adoption challenge. And I think that is in the pharmaceutical space increasingly clear, even though there's still a couple of years of research down the line. Okay, so these just two examples. So we work on many others. For example, corrosion research. For example, with Airbus. We work on the carbon capture materials. there's a technical element to it, like what technology makes the most sense. But I think equally important, there's a business questions. Where are the more valuable applications for our clients, but also for us? So maybe just let's see if there's some opinions from the audience on this. What do you guys think is one of the more impactful application areas? See your hands.
Hi, my name is Marianne. I was just wondering, when you're talking about business cases and use cases and make the most sense, there's a lot of different questions that come to mind with that. You mentioned earlier sustainability and climate change and the technologies that can be used for that. I imagine, just like in AI, there is quite a important it drains a lot of electricity and energy to use these computers, but there's a benefit that can be used on that. So I'm curious how that business case is not just economically, but on a sustainability level.
Yeah, so I think that is for sure something that we have been looking into. And so that was actually a project that our team did with the University of Delft to look at how quantum computing what quantum computing would mean for basically having better energy consumption or lower energy consumption for specific use cases. And that was the output of the research project that we did, that for specific, very specific non-time critical problems, a hybrid solution could work and deliver a more sustainable solution, because you could use some of the bigger compute work packages that really drain a lot of energy and lead to a lot of energy waste. If you can bring them onto a quantum computer with lower energy usage and get solutions or get the outputs while using less energy, because you can run them on quantum computer, then you have some kind of value out of it. So those are obviously just very early stages of that. It also depends on how the quantum computers will develop, and there is a lot of open questions, but there is a clear way how that could be of value. And so that was the whole research project that we did around it, and that we have done together with University of Delft. I'm not actually sure if the final paper of it is published. Julian, do you know that?
I think so. I think we can copy the link in the chat. And so maybe one thing to add. So indeed, there's potentially different benefits. There's potentially quantum computers could be cheaper to run, given you compare them with the same sort of task on a classical computer. They could be more energy efficient, or potentially they could simulate something that to a higher accuracy what a classical computer wouldn't be able to do. Specifically on the energy advantage, I think on the one hand, I think it's clear if we look at the explosion of parameters in machine learning models that we need to come up with some clever new approaches that are more energy efficient than the current way we do LLMs, right? It's just not sustainable to keep doubling the number of parameters every few months or so. And so who knows, maybe quantum computers could play a role in that. And I think it's evident to me that at least new compute technology will play a role in that. On the other hand, I'm always a little bit skeptical on green quantum computing, because the reality is that these quantum computers will be a co-processor to larger tasks. And the reality will probably be that in practice, we will just use more quantum computers and more classical computers, and in the end, the energy consumption will increase as well. I think it's called Stevens paradox, right? At the moment compute becomes cheaper, we'll just use more of it instead of less. But yeah, it will allow us to do new things, address new challenges, maybe build better batteries, and I think that is something that definitely will help humanity in many ways.
Yeah, I think that's a very interesting a conversation to be had about this paradox, because we had already also discussed this in regards to the aerospace sector, because we were talking about like better fuel, or if we could if there were solutions that would deliver like a fuel that's less harmful for the environment, would that be a good thing? Theoretically, yes, obviously it would be a good thing, but in the end, it would also probably mean that we would just start flying more instead of actually having a better impact. So there's always this paradox there. That's a bit hard to get around.
Yeah. And I think it's really up to us to make sure that we use it in a proper way. So in Capgemini, we are organized in a few different teams. So we have a team that really focuses on the low-level hardware implementation. We have a team that's really focused on the quantum chemistry and trying to figure out exactly the chemical reactions. And we have a team that focuses more on the advisory part. I think what is really a unique selling point for Capgemini is that we have those three, because in practice, you won't be able to have any quantum application in the next foreseeable future without a very deep integration between those three areas. You can't think about strategy without knowing the specifics of a use case. You can't run an algorithm but in the foreseeable future without going very deep into the low level of the hardware and optimizing everything you can such that you squeeze most out of the hardware. And so really all of these things are connected intimately. But at the same time, they all deserve their own attention as well. And I think that the advisory part is really something that we can really help our clients significantly with. That team is led by Ifti. So maybe Ifti, you can tell us a bit more about what is this advisory about?
Yes, for sure. So as Julian already mentioned, so the advisory piece is really meant to be the facing towards the client, help them really understand and address this technology. So we've heard that this technology is still a bit further out and there is still a lot of development necessary, but at the same time it has a massive impact, and there is roadmaps to how that impact will look like and how can we prepare, how can companies prepare, and especially the market leaders, the ones that want to stay in front of specific technologies, they also need to address it now, because quantum technologies is just such a different technology that implementing it in the future takes a lot of pre-work, takes a lot of work to really find the right solutionings for your specific problems and understand how quantum can play a role. And so that's where we've come in. There has been like asks from companies also to understand that, and we have created this offer around quantum advisory, how we call it, which is basically in 4 different parts. It has 4 parts to it. One is understanding the technology, so understanding the different parts of quantum technologies, how do they affect different markets, how do they affect different sectors, and what does that specifically mean. Then understanding the market for quantum technologies in general, what will it mean for a specific sector and how will they deal with it, what do they need to do to prepare for it. Then we get to organizational readiness, which is really the internal processes of a company. What does a company need to do to really be ready for that specific technology? And here we also obviously work with all technology. So post-quantum crypto plays a big role in that part. So we have done some projects with companies that want to create roadmaps around how do I become secure against quantum threats, and what does that mean for my organizations? How does that roadmap look like? So we really support them in understanding the technology, but at the same time also in experimenting with this technology. So there are companies that just want to experiment, want to do some small projects to really see the value of quantum for their specific area, but at the same time they are not really have the funding or the possibilities to invest a huge amount into quantum. And so because quantum technologies has these many different parts, we already highlighted some of them, but you really need to have the technology experts, you need to have some integration experts to understand how do you integrate it, you need to have the software developers that can develop like quantum algorithms. All of that is like a very complex process. And so we really help them with giving them access to our quantum lab, giving them access, allowing them to really use quantum and understand how quantum could look like for their specific industry. industry. And then the last one is really running successful projects. So there are already quantum projects out there. Some companies run their own quantum projects. A lot of it is publicly funded. A lot of huge research projects are publicly funded projects around quantum technologies. And so we support in that. We also run some of those bigger projects. I think one is mentioned in the next slide. If you could go forward, Julian. Oh, yeah. So this is the project that was mentioned. So it's a consortium. It's called Equality. So this is a European Union funded project, around 6 million in total budget for 4 years. And we have been working with companies like Airbus and Fraunhofer Institute. Pascal is the hardware partner. So Pascal is a specific quantum hardware provider that is also France-based, whom we have a good partnership. So with them as a hardware provider, with Airbus as one of the use case providers, we have been working on really understanding how can we run specific use cases out of the aerospace industry and the energy industry that have value, and how could they be run on quantum hardware, and how could those use cases look like. So those kinds of projects, and Capgemini is the leading and managing partner of this consortia. And so those kinds of consortia we've been doing in different parts of the world, and have been really making sure that we can help our clients, our partners, run really successful projects where we also get the outputs that we are going into it with, because in the end, those are still research projects, and that's very clear. So it's about maximizing the outputs of that research towards something that has value for us in the long term and really creates business value.
So I think this is maybe first, let me just recap a little bit of some of the key points that throughout the story, and then maybe we can just open up the mic and see what you guys think. So I think one of the key points that I would like to emphasize is that it is definitely still a couple of years out there, but the path towards value is getting clearer, specifically for quantum chemistry applications. But in order to get that to work, we really need to do our very best at multiple levels, right? It only makes sense to try to implement an application if we think about both the use case, the way it's implemented on hardware, and if we really do this in a way that it's valuable enough for applications, and we get organizations on board to go invest in this with us and to work towards adoption. And I think this is a fascinating period where we are in, because a couple of years ago that was different. We weren't really able to do any of that. It was much more exploratory. And so going forward in the future, that's also really where we will be working on to drive not just on the specifying the use case, but working closely and intimately with our key accounts on making sure that they will be able to implement this in their organizations. Maybe let me just stop there and see if there is some questions or some remarks or ideas. Did I capture all the key points well, FT, or do you add something?
No, I think you captured it pretty well. Nothing to add from my side.
So Harbin or Marianne, what do you think? Calling you out just to just get the discussion starting.
Well, I think it's quite fascinating what you're describing. I'm not really that well versed in quantum technology and the opportunities there, but it's quite fascinating to hear how close it is really, and what the potential could be. And I think perhaps we're not necessarily understanding the full impact when it arrives. But yeah, I found it really interesting when we look at different industries, rather than looking at it from a technical perspective. The very close correlation that you're describing with chemistry and the STEM values in that way is it has a lot of potential, which I find quite fascinating. Thank you.
Welcome. Yeah, I think that's in chemistry. I think it's more clear like how quantum solutions will be part as a tool alongside of other quantum chemistry solutions. So, for example, how we use a combination of molecular dynamics with quantum chemistry tools and DFT, and in combination with machine learning, and all these things will have to be combined into one solution. And I think one of the key risks is that companies do not see this in time. And then, you know, the startups and the quantum industry and academics, they're working on producing the quantum algorithms. But if companies haven't thought about, you know, integrating that within their organizations, they will risk, you know, the same risk, the same consequences they had with AI, right? Which is that even after the technology is available for many years, companies are lagging behind and are not able to keep up. And are outcompeted by the competitors who will, right? So that is really what we try to prevent, and helping at least our clients to adopt. All right. Any other questions, suggestions, or anything?
No, thank you very much for the preparation. It was very interesting, and it's good to know that we're already working on that and who are the responsible people for that, because it's going to be an area that's going to have a large impact. When it gets even AI and quantum computers together, is going to be also a huge leap forward. My question was, although you were talking about the whole time about chemistry, is also the pharma industry also within there? Yeah, it's
absolutely.
okay.
Yeah. So one of our key, chemistry is sort of our key focus area, because that's where the path towards value is the clearest. And within chemistry, it's a very wide range, right? So within chemistry, we do applications such as corrosion with Boeing and Airbus, drug discovery with AstraZeneca, with GSK, but also very similar projects with Unilever. Then batteries, so Saft and Volkswagen and others. Carbon capture materials, simulation with companies like Total and General Electric. So that all of this falls within the chemistry approach. Now, besides chemistry, there's many other potential applications of quantum computers.
Genetics, I would think so as well.
Yes, although I think it's a little bit trickier. So there's all kinds of genetics things that you could explore. You could maybe think about using optimization and trying to, or maybe machine learning and trying to capture some signals from genetics, and maybe not just genetics, but also proteomics and all these type of things. One of the topics that people talk about is things like topological data analysis, which could potentially be applied in this field. But I think it's a little bit trickier still. So really the systems that are most, where we think there's most potential is really for systems that have very strong many electron, very strong correlations across many electron systems. So really multi-reference strong correlation systems.
Yeah, thank you very much.
Oh, and one thing I forgot to say. So besides chemistry or genomics, genetics, and these type of things, we also work on optimization challenges where, for example, large maximum independent sets mathematical problems we could address. And we use specific hardware from Pascal for that, which is used for sort of analog simulation of large mathematical optimization problems. But I would say that's a bit more of wild card still. We don't really know if this is going to work out or not, but we just want to make sure that we don't miss out. All right. Then Ishmeet, giving back to you. I'm not sure if you have any final words.
No, I think it was a great presentation. So if anybody has any questions later on, you can always reach out to Ifti or Julian. Thank you for this wonderful presentation, both of you. Thank you everyone for joining.
Yeah, have a great day.
Have a good day.
Thank you so much for everybody. Bye-bye.